Yes. Green is on. Okay, and then stick this someplace. Yeah, then stick this in a pocket. Okay, great.
Yeah. All right. So is this okay with the mic and? So is it better now? All right. Okay, so good morning, everybody. Before being buttered up, let me say that I have at least some very nice handwritten notes, and they will be scanned after this lecture, so you can download them from the wiki, and I will certainly make an effort to type them as well. Okay, so I'm going to teach you about gauge-gravity duality, and so the organizers asked me to give a rather basic introduction to gauge-gravity duality, and yesterday at the reception I talked to a few people, and they said they would be very happy to have such a rather basic introduction. Also, I think my lectures tie in very well with the ones of Daniel, who's going to talk this afternoon, and also the conformal theory lectures, which we will have this week, and so I point out where there's relations to those, and some things I don't have to say because they will be said in the other lectures, and so that leaves me some time for something else. So now I need a piece of chalk. Okay, so please tell me if you can't read. Good. Okay. So I'm sure you all know that gauge-gravity duality is a major development in theoretical physics over the last 2 decades, and actually, so the original very super famous paper by Juan Maldacena was actually from 1997 in November, and so this will be 20 years ago now this November. So we can now say it, gauge-gravity duality at 20, and but of course, as you all know, it's a very vibrant subject still, and so I'm going to start by discussing some aspects of the original ADS-CFT correspondence, but then the idea is also to have some more general examples of gauge-gravity duality. Okay, so let me start with some extremely general statements. And so the first question which we are going to address is, what is a duality? And okay, so of course there are many different definitions of dualities, also depending a little bit on what area of physics and mathematics you're in, but in some sense they're all related. And so my approach is to take a definition within physics, which is pretty general. And the idea is as follows. So consider your favorite physical system, which could be theoretical, but also something in your lab. And then what certainly won't be the case for any physical system, but for quite a few, surprisingly many of them, is that you will actually have the possibility of having 2 different theories describing this physical system. So you will consider the situation you have a theory 1. So a theory means in theoretical physics that you have an action or a Hamiltonian, depending on whether you do particle or condensed matter physics. And you discover that this action or Hamiltonian describes your physical system. And then consider the case that there's a different action or Hamiltonian, which is a theory 2, which might be made out of completely different degrees of freedom, and which is given by a different action or Hamiltonian. And you discover that this theory, although it's made of completely different degrees of freedom, also describes the same physical system. Now, of course, if this situation is present, then obviously there must be a relation between these two theories, and this relation we are going to call a duality. So if this is the case, then we say that the two theories are related by a duality. Okay, so this will be my definition of duality. Okay. And of course, there are really many examples of this in physics. And so let me give you just the names of examples which are not gauge-gravity duality and which have been around for a while. So one is in two-dimensional quantum field theory. And so this is really a well-known example. And let me just give you the names. So there you have two theories. One is the so-called massive stirring model. And this will be due to the so-called Sine-Gordon model. So this is an example relating to quantum field theories in two dimensions. Then, of course, there's a very famous duality, which is the so-called monotone and olive. Electric-magnetic duality. Which plays a role in particular for NX24 super Young-Mills theory, which we will discover in this lecture, of course. And yet a third example are S and P dualities. In string theory. Okay, so just to show you that this is something which is quite common in physics. And so now, what is special about gauge-gravity duality then? So what is special about gauge-gravity duality is that, okay, so actually, can you read if the blackboard is down here, or should I? The people at the front are nodding, but the ones at the
very bottom.
Yeah, exactly.
Hard in the back.
Yes, that's what I thought. So maybe let me just.
There's two more boards also.
Yeah. Okay, let me go to the next board. Okay, so I'm about to explain what is special about gauge-gravity duality. So this relates, on one hand side, a gauge theory, which is a quantum field theory. And so the main feature of the theory is that it doesn't have any gravity. It's just a standard quantum field theory in flat space. But then it relates, so the second theory in the sense of my definition, which I have written on this blackboard here, this is related to a string theory, or slash a gravity theory, with string theory certainly being a theory which also contains gravity. Sorry. So we have this really remarkable situation that our duality relates a theory which has no gravity but which is a quantized theory, and on the other side we have a theory which has gravity. And that makes it special also compared to the other dualities which we have there. And so of course that raises lots of interesting questions about the nature of gravity. So I should say that this is of course of intrinsic interest for gravity and its relation to quantum physics. So we could ask this question, is gravity just an emergent theory, given that it seems to be equivalent to just a quantum field theory in flat space? Well, I think this is a question which there's under a lot of debate. I think we shouldn't forget that, of course, here we are considering rather special examples of quantum field theories and gravity theories, not all of them, but nevertheless, certainly this poses important questions about the nature of gravity. So this is of intrinsic interest for gravity and its relation to quantum physics. Okay, so you could ask the question, is gravity emergent in some sense? And I think that brings a link to what Daniel is going to tell you about in his lecture. Okay, so now in the current research, which is done in gauge gravity duality, there's essentially two directions. One is a more fundamental one in the sense of understanding this duality better, and so I should emphasize already at this point that so far gauge gravity duality is of course a conjecture. There's no mathematical proof of this duality, and I think one point of my lectures is also to explain to you why it is so complicated to prove this, but on the other hand, why from a physical point of view it's very natural to have this duality. So it's hard to have a mathematical proof, but from a physics point of view it's very natural. And and apart from this fundamental questions, there's also, of course, many applications, so which will be covered by Oliver de Wolf in his lectures. But let me just give you a quick outlook why these are interesting, or what is the punchline about this. Okay, here I should say this leads to fundamental questions. Okay, by the way, I should say there's more here on my sheet than what I'm writing on the board, so it's probably worth afterwards having a look at my notes. Okay, so the application comes from the fact that in a certain limit, which I'm also going to discuss, this duality involves strongly coupled gauge theories. And that's, of course, interesting because these are usually hard to treat in physics when you can't apply perturbation theory. And so you have this new approach to actually studying strongly coupled quantum field theories by mapping them to a classical gravity theory. So in a certain limit, which I'm going to explain to you, so a strongly coupled gauge theory is mapped to a classical gravity theory. So a classical gravity theory is, of course, general relativity. Okay, so this is very useful for strongly coupled systems for which perturbation theory is not applicable. Okay, of course there are other techniques for studying strongly coupled quantum field theories. However, gauge gravity duality has this possibility that you can very easily look at non-equilibrium situations. You can look at finite temperature, you can look at finite densities, and which add to the complication of studying strongly coupled systems. And so this is certainly something that is complementary to the approaches which are available. It's very interesting to compare them with other approaches and combine these approaches together. Okay, and so before going into any calculational details, I would like to discuss one example where, in what sense, these applications are of interest. And so this example is in relation to collective excitations versus so-called quasi-particles. So quasi-particles, what you have in a strong, in a weakly coupled theory, when you can do perturbation theory, and generally what a quasi-particle means that you have a one-to-one correspondence between those fields of the free theory or the states of the free theory and the states of the weakly interacting theory, and so that helps you to establish lots of techniques. So one is this Landau Fermi liquid theory, for instance, to address physics of weakly interacting particles. However, in strongly coupled systems, this is no longer the case, and you will have some collective excitations, and then you can't use this map anymore. And so here, this is where gauge-gravity duality kicks in, because it provides a new approach to studying these collective excitations. And so these you can actually map to the so-called quasi-normal modes in the gravity theory. So quasi-normal modes are the complex eigenfrequencies of fluctuations about the solution of your classical gravity theory. And so they're just quasi-normal, or they're complex because you can consider the situation when there's dissipation, and some of these excitations are actually going to decay. So this is very nice. This is a technique actually which is used a lot in general relativity. For instance, the LIGO experiment, which is now very famous and discovered, gave a direct evidence for black holes by studying gravitational waves emitted from black hole mergers. They also use this quasi-normal modes. Of course, here these quasi-normal modes won't be in a standard flat space or, say, de Sitter space classical theory, but here, of course, we will study theories which are in anti-de Sitter space, which is unlike the real world, but nevertheless, you can use very similar techniques, and they will provide you a lot of information for studying these collective excitations in strongly coupled field theories. Okay, let me make a quick summary of this here. So, okay, so quasi-particles. So in weakly coupled theories, these are in one-to-one correspondence with the states of the free theory. And so this is no longer the case. In strongly coupled theories, and then here now the idea is to use a map between collective excitations in the strongly coupled Q with T, and these will be mapped to the so-called quasi-normal modes of fluctuations about the gravity background. And so these quasi-normal modes, so usually they are abbreviated by Q and M. So the Q and M are complex eigenfrequencies. And the imaginary part tells you about the decay of these modes. So that's because they're not just normal modes, they're quasi-normal modes, so this means they can decay. Okay. All right, so that was just an example to give you some motivation why applications are interesting. But now what I plan to do in this lecture is to turn to the best understood example of gauge-gravity duality, which is, of course, the ADS-CFT correspondence. And in particular, I will use this, well, I would say most studied example of the ADS-CFT correspondence, which involves NX24 super Young-Mills theory. And so I will present this correspondence to you and then explain what the original motivation of Maldacena was to propose this, and this will involve some concepts in string theory such as D-branes. And so I will present this argument to you probably tomorrow. And today I just want to review all the ingredients you need to know to really understand this correspondence. So the way I'm going to proceed is to first write down what the correspondence is, and then explain the various ingredients which we have. Okay, so before I proceed, let me quickly say, the reason I guess why I'm here is because I wrote this book on introducing gauge-gravity duality together with my former student Martin Ammon, who's now assistant professor. And I'm using the book to prepare these lectures, but it's here, so if you want to browse, you're welcome to come after the lecture and take a look. And so most of the things I'm going to say you can find in there, actually. Okay. All right, so as I said, we will study the best understood example of gauge-gravity duality . And so this is the ADS-CFT correspondence. Okay, so gauge-gravity duality is a much more general concept than just the ADS-CFT correspondence itself. And so I mentioned to you that it's going to be really hard to actually prove gauge-gravity duality, or even let alone prove the ADS-CFT correspondence, and I'm going to explain to you why. So one question is, so definitely the ADS-CFT correspondence itself originates from the string theory argument, which I'm going to present to you. And if you asked me about 10 years ago, I would have said to you, well, I think to actually prove the ADS-CFT correspondence, you have to find a proof within string theory. And so I strongly believe that this is a concept which only makes sense in the context of string theory. However, given the research in the last 10 years, I think I changed my mind, and it could well be the case. So again, I think what I'm saying now ties in with the lectures of Daniel this afternoon, that this is a concept which is much more general than string theory. And maybe there's other ways of proving it. And but of course, this is current research, and the answer to this question is not known. Nevertheless, I still think that this example and its string theory origin really gives a very well understood example where it's very clearly motivated why these two theories should be related to each other. And so that's why I really want to emphasize and present the string theory argument, because then you can really understand, well, okay, there's no mathematical proof, but since I think most of you are physicists, you will say, okay, I'm a physicist, and it's just got to be true. I mean, there's so good arguments, it's just got to be true. And I will give you some extremely good arguments why this makes sense. Okay, so that's why I'm going to focus on this. Of course, in the view of the things I said before, okay, to put it in a very negative way, this is a kind of slightly academical example, because of course the virtue is that it has a huge amount of symmetry, but since it has such a huge symmetry, it's probably not realized in nature. I mean, this is always what you have in physics. Either things are very beautiful and symmetric, or they describe the things in the real world. But if you have two things at the same time, this is very rare. And most of the times you have to somehow make a choice. So we will start with a super beautiful, super symmetric maybe a little bit of mathematical interest example, and then we will see how we can go from there to get to these more general examples, which have a lot less symmetry than this original one. Okay. Oh, sorry, yes.
Just about, like, generally what gauge gravity
Yeah.
like the gauge part of that, a fundamental piece of it, or say, like, I would understand it if gravity
Okay, this is a super interesting question. I think the idea of my lecture is to spend 5 hours to explain precisely the answer to your question. But maybe to just give you a quick outlook. So, okay, so here gauge gravity duality means, I guess as I explained before, so this is a quantum field theory which is a gauge theory and has no gravity. And and the conjecture is that this will be related to a gravity theory. And I will give you some example for this, which is the ADS-CFT correspondence in this example of NX24 super Young-Mills theory. Now, I was just mentioning these very good reasons why physicists should believe that this is true, and one of which is, of course, this aspect of holography and the holographic principle, and I will certainly mention that also in the course of this lecture. So, since you're asking, I'm saying, okay, there's these very good reasons why this should be true, and one of them, there's a huge amount of symmetries in both these theories, and they coincide. This is one argument. The second argument is due to this holographic principle. The amount of degrees of freedom is the same, or I should say per unit cell, is the same in the two theories. So I have two theories which have the same huge symmetry, and I know they have the same amount of degrees of freedom. And as being physicists, I think then we should just believe that these are the same theories. Okay, that's going to be my argument. So thanks for this question. And so I want to be much more precise about how this how this came about by using the string theory argument. Okay, I think you're probably asking about some aspects which Daniel will cover in his lecture, which are slightly complementary to what I'm going to say. I should say that, yeah. No, this is the next thing I wanted to say. I should say that here I'm looking at this example where you have a gauge theory, but there's examples where this is not a gauge theory, but still a quantum field theory. And I think the best understood example is this higher spin theories, for instance, where there you have an ON vector model and a 3D ON vector model, which is it's a quantum field theory, it's not a gauge theory, which also has a duality with some gravity theory. But there it's much harder to understand how this is embedded in string theory. So for the sake of the string theory argument, I will focus on the case of having a gauge theory. But as you correctly said, there's also examples of gauge gravity dualities where the theory is some other quantum field theory, which is not a gauge theory. I might touch upon those later, but okay, for the sake of the present argument, I will focus on gauge theories. Just because it's the best understood example. And then later, we can see if this can turn into some quantum field theory gravity duality. And as I just mentioned, there's examples for this as the higher spin dualities, for instance. Okay, very good. Are there other questions at this stage? Okay, so let us study the well-known example in which the CFT, okay, I should recall that CFT means conformal field theory. So in this best understood example, your gauge theory is a conformal field theory, but later we will see that there's examples where you can actually break this conformal symmetry, and this will give you some more general gauge theories. So, and we study the case where this is n equals to 4. So this is a curly n, and here is a straight n. There's two n's in this name. Okay, super Young-Mills theory. So which is a particular quantum field theory in 3+1 dimensions, which I'm going to explain now. Okay, so just for completeness, just let me remind you that ADS, of course, stands for anti the sitter space. And I'm also going to explain to you again what an anti-de Sitter space is. I should just say de Sitter was a Dutch physicist who was a good friend of Einstein. And anti just means that you turn around a particular sign to become negative. So this is a hyperbolic space with a negative cosmological constant. So it's a very well-defined space, but it certainly is not related to the metric which we see in our universe, which is more a de Sitter space. Okay, but I will come back to this later, so let me start by explaining this theory. So first now I have to wipe the blackboard, and then the second thing is let me just write down the particular example of gravity duality and the ADS-CFT correspondence, which I'm going to discuss now. Okay, I guess this is the thing to wipe the blackboard.
There are also erasers.
Yes. Yes.
There are erasers there.
All right. Okay. This thing? Yeah. All right. Okay. 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 Well, I could just use that one. Okay. All right. So after this introduction, let's get more concrete. And so let me just state of this the original ADS-CFT conjecture. So of Maldacena in 1997. And well, if you look at his paper, there's several examples in that paper, and let me focus on the one which is the most studied, I think, although there's other examples which are also extremely well studied. So we start with this NX24 SUN super, so SYM means super Young-Mills theory, which has, so this is a theory which, due to its huge amount of symmetry, it has only one coupling constant, and so this I'm going to call G Young-Mills. And so the statement of the duality is, so this next line is extremely important. So the duality means that this theory is dynamically equivalent Okay, so this we will return to what this phrase precisely means later. So the original suggestion was that this theory is dynamically equivalent to type 2B superstring theory on the space ADS5, so it's a five-dimensional anti-de Sitter space times a five-dimensional sphere. Okay, so superstring theory is consistent in 10 dimensions, so you need a 10-dimensional space. And so we take this example here. And so there's a few comments to be added. So first of all, the string length in this string theory is called LS, and this is given by the square root of alpha prime, where alpha prime is the inverse string tension, and so this has a coupling constant called GS. Let me get some more chalk. And so then this hyperbolic space, the ADS5, has a particular radius of curvature, which is called L, and it turns out that this length scale will be the same for both factors here, for the ADS and the S5. So for both ADS5 and the S5, so this will be called L. And so there's another ingredient is that we need N. So N is this N as in the SUN theory. So there will be N units of 5-form flux. So this is something I'm going to explain tomorrow what this means. So we have a 5-form flux going through this S5. And so now there's an important relation between this coupling constant of the super Young-Mills theory and the coupling constant of the string theory, as I'm also going to explain tomorrow. So the Young-Mills coupling of your field theory squared is equal to the coupling in the string theory. And then there's another super important relation is that twice the Young-Mills coupling squared times N. So this can be abbreviated as lambda, which is the so-called 't Hooft coupling, which will also be extremely important. Will be equal to this radius of curvature of the ADS space divided by the string tension squared. Okay, so both of these relations on the left-hand side have a relation in a quantity in the gauge theory, and on the right-hand side they have an object in the string theory. Okay, so coming back to what I said in answer to the question which came earlier. So one motivation why these theories should be related to each other is these two theories have the same huge symmetry and the same amount of degrees of freedom. Yes.
So this relation, does it come just from dimensional considerations, or there is some way to systematically derive this?
Sorry, let me just write the end of the sentence. Sorry, we'll come back to this. So this is related to this holographic principle. Okay, so this is the motivation for identifying these theories, and I will explain in more detail where this comes from. Now, your question, so which relation were you talking about? This one?
For example, the second one, is it just
Okay, so this tomorrow when I talk about string theory, I'm going to actually show where this relation comes from. And so this comes from the study of D-branes in string theory. And so it turns out that this N is actually also related to the number of D-branes which is stuck on top of each other. And of course, there's also some dimension. Of course, this has to be a dimensionless number, certainly. But okay, let me answer this question tomorrow. So a large portion of the lecture tomorrow will be explained exactly where this relation comes from. And so you really need to look into string theory to understand where this comes from. And I will do this tomorrow. Good. Okay. Yeah. As I said, I mean, here I'm just telling you what the proposal of Malacena is. But now an essential part of my lecture this week will be devoted to explaining to you everything what is written on these two blackboards now. Okay, so here I'm giving you a summary. So I want to first now we are going to study the theory at the top. So what is the features of this particular conformal field theory in 3+1 dimensions? Then I'm going to explain a few things about the string theory and also its supergravity limit, which will be super important. Then I will say what I mean by this is dynamically equivalent to. And then also I'm going to explain where these relations come from. So you should view these two blackboards more as a program for what we are going to do in the next couple of lectures. And so the idea is, okay, first I'm going to explain all the ingredients separately. So I have to explain what the theory is. It's a conformal theory. And so it's an SUN gauge theory. At some point, I mentioned a limit, so we will take the limit where this rank of the gauge group will go to infinity. So I will explain all these things now. Then we have to remind ourselves what an ADS space is. And so once I explain all these ingredients, then I will explain what the two things have to do with each other. Okay. So this is so these two blackboards are planned for the next couple of lectures. Yes. Okay, this is again a super good question, and I'm about so okay, all the things you're asking this is what I wanted to explain to you. Since you're asking, as written on this blackboard, this holds for all n, but this statement is so general that you can't actually do anything with it. So to actually do some explicit calculations, we will take the limit where n goes to infinity. So to answer your question, there's different levels of the ADS-CFT correspondence. There's a strongest form, which is the one written on this blackboard. Then there's the strong form. The strong form is when you take n to infinity. And then there's something called the weak form. And in the weak form, you take the string length to 0, which means you go from the string theory to a gravity theory of point-like particles. And in that case, you map to the strongly coupled quantum field theory. Here, I mean, this quantum field theory doesn't have to be strongly coupled in this general statement which I have written here. Okay, but this will come out as a particular limit, and this I will explain tomorrow also. Okay, so short answer to your question, as written here, it holds for all values of n. Okay, this is a conjecture. I mean, you can conjecture everything you like. So this is a conjecture. The conjecture is presented for all values of n, so the straight n, and all values of so for a finite value of the string length. However, as we see, to actually do something practical, we will have to take two limits. One is to send n to infinity, and the other one is to send this ls to 0. And both of which I will explain. Good. Okay, but this is all our program for tomorrow. And so what I was going to do now is just to review some aspects of the features of this NX24 super-Young theory, and then some aspects of this string theory and of the anti-de Sitter space. So for the rest of today, now I'm going to get much more technical. I want to describe the features of the two theories which are involved in this duality. Okay, so our program is to explain everything which is on that blackboard. And so the first thing is I'm going to explain a little bit again what a CFT is, which is involved in the ADS-CFT correspondence. So and you will have these lectures by Yin this afternoon about 2D CFTs. But of course, NX24 super-Young is a 4D CFT, and which is a little bit different from 2D CFTs, because there you don't have an infinite amount of conserved quantities, as is the case in 2 dimensions. Mm-hmm. Yeah. Yeah, again, can I postpone this question to tomorrow? Because I think tomorrow a big portion of the lecture will be devoted to explaining precisely where this relation comes from. So I note your question, it will be answered, but let me postpone this to tomorrow because I really have I have at least 3 pages of notes for the derivation of this equation. So this will come tomorrow, so just bear with me until then. And let me do some further simple things first before coming to that step. Okay, so let's very briefly recall what a CFT in more than 2 dimensions is. Okay, so this consists of fields which transform covariantly under suitable representations of conformal coordinate transformations. Okay, and let me just really briefly remind you that these leave angles invariant locally. And and they're defined by a transformation of the line element in the following form. So you have a scalar function which for some notational reason is called omega to the -2. And so the square of the line element is essentially multiplied by some x-dependent factor, so which is of course more specialized than having a general Lorentz transformation, where here you would have 2 Lorentz transformations acting on these indices. But here in this case we just have a scalar function. And then you can write this infinitesimally so infinitesimally we write this function capital omega in an 1 minus some function sigma of x, where sigma is an infinitesimal function, and then we have an infinitesimal coordinate transformation where x prime of mu is the original x plus some vector v of x. Oops. And then this, if you insert this into this equation, so let me call this star. And so infinitesimally star becomes the so-called conformal killing equation, which looks like this. So you have these derivatives acting here, and then you have this function sigma. And so this is called the conformal killing equation. And so in more than 2 dimensions, again, so the case d equals 2 is very special. This equation is solved by transformations which are most quadratic in x. And let me just write those. So these are the translations where you just have a constant vector. Then you have rotations or Lorentz transformations depending on what signature you're working in. So this omega is an antisymmetric matrix. Then you have scale transformations, where you just multiply x with some constant factor lambda. And then there are the so-called special conformal transformations, and these are just the quadratic solutions to the conformal killing equation. Okay, so, and as you can see, if you count the number of parameters, when d is equal to 4, this gives you 15 independent parameters. So this means if you have a conformal field theory which is invariant under these symmetries, you have 15 Noether currents associated to the symmetry. Okay, so this is the coordinate transformations, but for a conformal field theory we need to know how the fields transform. And so for this we have to write down an algebra which is related to these transformations. Okay, so first of all, I should say there's a symmetry group associated to these transformations, and in more than 2 dimensions, this group is SOD, 2 if you work in Lorentz signature, or it's SOD plus 1, 1 if you work in Euclidean. Okay, so why am I telling you about this? Because as I advertised on the blackboard on the left, ADS-CFT works because there's a huge symmetry, so let me explain to you what this huge symmetry consists of. So one essential part is, of course, the conformal symmetry, which is given by this group. And then associated with this group, we have a conformal algebra. And so this actually consists of the Poincaré algebra because you have translations and Lorentz transformations. And this is supplemented by the following relations. Okay, let me write them. There's a couple of them, but I think it's worth writing them down for definiteness, such that you know what I'm talking about. So this J mu nu is the generator of the Lorentz transformations, and then there's a generator for these special conformal transformations, which is called K. And so here the commutator gives you I times eta mu rho K nu minus eta nu ray K nu. Then there's a generator for the scale transformation or dilations, which is called D, and this has the following commutation with P, which is the momentum or translation generator. And then we have a relation for how the dilation or scale transformation operator commutes with the generator of the special conformal transformation, so this is minus I K mu. And then, so D actually commutes with the Lorentz transformation, so this just gives you 0, and 2 of these special conformal generators, they also vanish. And then finally we have a relation of how the K's act on the P nu, so this is minus 2I eta mu nu times D minus J mu nu. Okay, so now if you have a conformal field theory, it means you have to look at particular representations of this algebra, and your fields have to transform covariantly under these representations. Yeah? Oh, yeah. So for now, so I should have said this. Okay. So here we work in flat space. And okay, so I'm simultaneously, okay, so I think this equation you can solve both at the level of Euclidean or Lorentzian signature. I think this algebra probably is for the Lorentzian signature now. Okay, so we are just in flat d-dimensional space for now. Okay, so then once you know how what your algebra is, then you have to look at representations of this algebra. And to do this, we start with a postulate, which is if we look at the commutation of this scale transformation operator with some field. Okay, I'm writing a scalar field here, but this is true more generally, also for fields with indices. And we take this at position x is equal to 0. Then we want this to be minus I delta times phi of 0 for any phi of x. And so this actually implies that this capital delta is the scale dimension of the field. So phi of x will go to some phi prime of x prime, and this will be lambda to the minus delta phi of x if x goes to x prime, which is lambda times x. So this means delta is the scale dimension of phi, and so we have an infinitesimal transformation. So associated to this transformation, which is just defined as this commutator. And okay, so here I gave you the relation for x being 0, but by applying the translation operator, you can, from this result, infer the result for any x. And the result for any x will be minus I delta phi of x, and then you get a term from the translation, which is minus I x mu del mu phi of x. And there's a similar transformation for the other conformal transformations. Okay, so from this transformation under the scale, the scale transformation, then you can actually infer what the correlation functions in this theory are going to look like. And so let me show this to you. For a scalar field, sorry. So these transformations give rise to so-called conformal Ward identities. So a Ward identity is generally a relation in quantum field theory which expresses symmetries which are present in a quantum field theory, and in this case it's for the conformal symmetry. And so then in particular if you have a correlation function with n entries, so then you have to transform. So you just apply the chain rule and you do the transformation for all of these fields. So then essentially you get. So if we have a field phi1 at x1, phi2 at x2, and then at the ith position you have to do this transformation. And so the symmetry asks that this will be 0. Okay. And so then you can actually solve this equation, in particular for scalar fields. So if you look at the transformation properties under this dilation operator, which I've written over there, so this implies for the 2-point function that. So here we have a 2-point function, so a field. Now this is our scalar fields. Now a field phi1 at position x1 and a field phi2 at position x2. And if you solve this word identity, then you find that this is actually fixed up to a constant, and and also it's non-zero only if the scale dimensions of the two operators coincide. So if the scale dimensions of operator 1 is equal to the scale dimensions of operator 2, and you call this just delta, then you will get this result. And if these two are different from each other, then you just get 0. So, and we see an example that the conformal symmetry actually fixes the correlation function up to a very small number of parameters, which in this simple case is just one constant. Yeah? Yeah, okay. I guess you're right. Okay, so then I should rub off this data. Okay, thanks. So yeah, if you combine, yeah, you're completely right. If you combine the scale transformations with this transformation for the special conformal, okay, which I'm about to write down, then that's true. You imply this relation here. Okay, so now let's consider the other transformations and also, and let's consider fields with spin. Okay, so for fields with spin, so if they have some indices, we actually can write the infinitesimal transformation for all these conformal transformations. So V stands for all infinitesimal conformal transformations. So you just insert this V, which I think I just rubbed off. Okay, so up to this quadratic term, and this is given by a variant of the Lie derivative, which is called L curly L with index V, and so this is given by the following expression. So first you have your vector V of x, which solves this. So this is the solution to this conformal killing equation, and then you have this term where you look at the divergence of V, and now there's one term which takes care of the spin, which is minus I half here. So you anti-commute these indices, so that's why I put these square brackets, and then you multiply with a Lorentz generator. Okay, so and then if you insert this into the transformations there, and then you get the transformations for all solutions of this conformal killing equation. And then you can actually study correlation functions not just of scalar fields, but also of vectors, tensors, and so on. But in all of these cases, you actually realize that so in a CFT, so even if it's in more than 2 dimensions, the correlation functions. So I think in particular, I should say the 2 and 3 point function. So for 4 point function, it becomes more complicated because you have cross ratios. They are fixed by the symmetry up to a small number of independent terms. So there are some independent forms made out of the coordinates which you can write, and but the symmetry is so strong that these correlation functions are almost fixed by the symmetry. Of course, there's still some freedom depending on which particular quantum field theory you're actually looking at. Okay, so then one further thing. How am I doing on time? Actually, because I started late a few minutes. 20 past? Yeah, okay. I'll stop at 20 past, okay. And okay, so then something extremely important in view of the ADS-CFT correspondence. So for the ADS-CFT correspondence, so far I told you, well, here we have this conformal field theory, and here we have the string theory or gravity theory, and they're supposed to be dynamically equivalent. Okay, that's very beautiful, but it's not very practical in terms of calculations. But really, ADS-CFT tells you that you have a one-to-one map between operators in your quantum field theory and the gravity fields in this gravity theory. And it's actually the symmetry which tells you which entry in this quantum field theory is dual to which entry in this supergravity theory. And the dictionary is given by representations of the symmetry. And so because we look at this NX24 super-Young theory, it's not just the conformal symmetry, but it's also the supersymmetry which determines these multiplets. But already for the conformal field theory, we actually see that the fields in this theory organize in multiplets, and that will be extremely useful for establishing this dictionary between the two sides of the correspondence. Okay, so in a CFT, the fields organize in multiplet, and let me just show you how this works. So there's something called the quasi-primary fields. Why are they called quasi-primary? Well, primary fields you will discover in your lecture on two-dimensional conformal field theory, and in this high-dimensional case, there's some remnant of this structure which you have in 2D, and that's why there's this word quasi-primary here. And they satisfy the following commutation relation. So if you take this generator of the special conformal transformation, and you take one of these quasi-primary fields, then this commutator is supposed to vanish. And so this actually now defines the fields of the lowest scaling dimension in an irreducible multiplet of the conformal algebra. So this defines the fields of lowest scaling dimension in an irreducible multiplet of the conformal algebra okay, and then there of course you can also generate all the other entries in this multiplet, which are defined by this particular field phi, by applying a kind of ladder operator if you want. So all other fields in this multiplet, so the one given by this particular field, so they are called the conformal descendants of phi are obtained by acting with the operator p mu on the quasi-primary field. Okay, and so you have this multiplet structure, and this will be very important. So this will be for establishing the so-called field operator map of the ADS-CFT correspondence. Because then you can organize your fields in the field theory and the fields in the gravity theory under the same symmetry which is present, and then you have this one-to-one dictionary between the two sides of the correspondence. Okay, to conclude, let me make one final remark because we want to talk about n^4 theory. So, a necessary condition for quantum field theory to be conformal is that it is scale invariant, because the scale transformations were actually part of the conformal group. And so this means if you have a quantum field theory and you want scale invariance, this means that the beta functions of your theory must vanish. So a necessary condition for quantum field theory to be a conformal field theory is that its beta function vanish. Okay, so if they vanish just at isolated points in the coupling constant space, then well, you have a conformal fixed point. But in n^4 theory, this is actually this. There's only one beta function, and it's identically 0. So this is indeed the case for n^4 superuniverse theory. For which, so there's only one coupling, and the beta function of this coupling just vanishes identically. So there's not even just a isolated fixed point, but it's identically 0. And so this makes this a prototype example for applying this conformal structure, and that's why it's one reason why it enters the ADS-CFT correspondence. Okay, So I'm about halfway through of explaining the properties of NX24 super young MILFs, which are relevant for understanding the correspondence. So what I'm going to do tomorrow, I will quickly finish this by telling you how this NX4 supersymmetry enters the game. Okay, so here we have supersymmetry. And actually what this amounts to is to have an extension of this conformal algebra, which I have just written, and there will be some more generators which then have anti-commutators because this has fermionic generators. Then I just quickly write down what the Lagrangian for this theory is. And then I tell you about this limit when this n becomes very big. And okay, then I just write down what an anti-de Sitter space is, and then I turn to the string theory side of the correspondence. And so let me go back to my blackboard, which I carefully made sure not to wipe before. So okay, so the purpose of the lecture is to explain what is on this blackboard, these two blackboards. As you can see, I started by explaining what a CFT is. So I finished this first tomorrow. Then I explain what this is. And then to understand a little bit about string theory and how these things are related, I will talk about D-branes. And then I will take these various limits which I mentioned. And so that will then enable us to understand what means is dynamically equivalent. Okay, so you can see what the plan for these lectures are. Thank you very much. Any other questions? Maybe. I think you could possibly imagine something. I mean, okay. So if you have conformal field theories just at isolated fixed points, then you can have anomalous dimensions for certain operators, and then it certainly can become non-integer. I think what you're thinking about is that when people test the ADS-CFT correspondence, they usually use some very particular kind of operators, which are just these quasi-primary operators. And in the superconformal symmetry, so far I just talked about the conformal symmetry, but when you have the superconformal theory, there's some operators, quasi-primary operators, which have protected dimensions, and so those are integer. And when people talk about ADS-CFT, they usually use these operators to provide a simple test of the correspondence. So this, I think, might seem that in a conformal field theory, operators are always protected. But I don't think this is the case. I mean, you can certainly have anomalous dimensions which change this to a real value. I would say yes, yeah. Yeah, all right, okay, good, that's true, yeah. Okay, I agree, yeah. Yeah, okay, first here and then.
I think in your book, the relation between DYM and DS factor 2 pi.
Okay, thanks for the advertisement. Okay, let me say that there's different ways you can define this. It depends on how you define this lambda. Okay, so I should say that different people do it differently, and you can absorb some factors in the definition of lambda. Okay, I haven't written an equal sign here yet. Okay, this I will do tomorrow. Okay, so I think that there's a normalization issue. There's different people have different choices. Okay, and in the book actually this took a lot of time to use the same convention in all the chapters of the book. I mean, this took forever. So, but okay, thanks for pointing out.
Maybe just one more question, and then we'll take it.
Yeah, here is a.
So I know that
Yeah.
diffusion, but normally I see diffusion, whereas yes, I step on black hole. Does that make sense?
Okay, so good. I think so. First of all, I think. All right. So you're thinking about quasi-normal modes in the case of black holes, so when there's a finite temperature.
Yeah.
And okay, certainly there's a UV-IR relation in the ADS-CFT correspondence. That's certainly true. So when you are in the UV in the field theory, you're in the IR in the gravity theory.
Right, but well, I'm
yeah.
UV, the large radius, so in the field theory, I would think that you could into the UV field theory will cross some even the boundary force. But instead, it seems like the quite well picture of the.
No, it's more things falling into the black hole, actually. So,
Cool.
yeah.
I know that's why it's backwards. As an IR effect, the field theory stuff all the black hole.
Okay, so I mean, okay, so probably I will come back to this later in the week, but okay, so hydrodynamics is about long-range fluctuations where you have low energy degrees of freedom, and it's an effective theory.
Yeah.
And certainly that's exactly also what you consider here, because you just look at the frequencies of fluctuations in that limit. So yeah, I do think it's all consistent, but thanks for putting this out. I will come back to this on Thursday when I talk a little more about the applications.
So why don't we take a break now? There are refreshments out here in the hallway. We'll reconvene at 10:45 for the next talk. Let's thank Johanna again.